Overfitting, the ultimate analysis.
Today you are going to see an introduction about generalized additive models, known as a GAM, but we are going to be focused on the overfitting. As you are going to see, GAM can fit on the data really well, and sometimes it's difficult to know what is the limit between the optimum model and the overfitting model. In this video tutorial, you are going to learn how to use a very sophisticated geostatistical analysis in order to avoid the overfitting when working with big data sets and you want to use the generalized additive models. Remember that this lesson is part of the 4th geostatistics course about Kriging and cokriging interpolation and mapping. And if you want to have full access to this course, just go to the GeoRGV community website at gscourse.online, go to courses, get enrolled at the 4th geostatistics course. Then when you are enrolled, you are going to have access to all the content. Then you can press just start learning. And here you have the first video, that is the introduction. Then you have the first lesson that it was about ordinary Kriging. You have the second lesson that it was about universal Kriging. And now we are working on the third lesson. In the third lesson you have already several videos. The first one is the introduction about the regression Kriging. The second one, it was about how to create a grid using a shapefile with R and QGIS. Then the next video is about ordinary least squares. The next one is about generalized least squares. And for today's lesson, you are going to have the video related with the generalized additive models, and we are going to be focused on the overfitting. Also, in each lesson, you have the folder to download the scripts that we are using during the lesson, and also in this case I added the digital elevation model if you want to reproduce the same results as I get in this exercise. Also, you can follow us at the GeoRGV YouTube channel, and here you have also all the content that you have on the courses, but in YouTube there are some restrictions. But if you are interested in the courses, you can still follow these courses through YouTube. Now let's go to see a summary about what we are going to do today. First, we are going to load a digital elevation model, DEM, based on LiDAR data. Then we are going to cut this digital elevation model, and from this data we are going to extract 200 samples with the elevation of the terrain. The goal of doing that one is to have a spatial data that is based in a real case. Then in this case we are going to have the X and Y coordinates, and also we are going to have the Z, that in this case is going to be the elevation of the terrain. But the Z could be anything, right? Could be the concentration of a contaminant, could be the groundwater elevation, could be the pH of the soil. At the end, it could be any variable. The interesting thing here is that we are going to pretend that we go to the field and we pick up different samples in this location. It is supposed that we don't have any digital elevation model, okay? We have just the samples. And with these samples, we want to create a model to predict the surface of the terrain, in this case the topography, right? Here we have a 3D model based on this digital elevation model, where you can see the tile of the topography. This LiDAR file, it's with very high resolution, and we can see a lot of details related with this topography. Also, at the end, we can compare the real X scenario with the prediction that we get with the regression Kriging using the GAM. That one is not going to be part of the video tutorial of today. Then after taking 200 samples that are going to be taken randomly, we can use the seed equal to 3. we are going to create a attribute table. In this attribute table, what we are going to have is the elevation, the coordinates x, and the coordinate y. Then we are going to export this table as CSV format. Then we can edit the table and import to RStudio. Then in RStudio, we are going to use this data to introduce the generalized additive models using the package mgcv. Then we are going to do an introduction based on the univariate and bivariate analysis. This is 2 dimensions and this is 3 dimensions. And then we are going to make a data partitioning. We are going to divide the original data, that is this one, in 2 different data sets. One is going to be the training, that is going to be the 75% of the samples, and the other one is going to be the testing, that is going to represent the 25% of the samples. Here we have a graph related to the original data, the training data, and the testing data. And for each graph, we have the regression line that is showing the trend of the data. In this case, we are working with the univariate. Then if we make some zoom over here, the important thing for us is going to be the training data and the testing data. And what we are going to do is to fit on the training data a model, okay? In this case, the model is the polynomial of first order. Then we are going to take this model and we are going to bring this model to the testing data. And we are going to use the model from the training data, that is this one, to evaluate the residuals in the testing data. Then we are going to take the residuals here, the distance from here to the observation is going to be the residuals, and then we are going to calculate the residuals of the testing data using the model from the training data. At the end, what we want to see is how efficient is this model with a different data set, but this data set is from the same location. And what we want is a model that is general, that not only works with this data set, but also works with different data sets from the same location. We know that this model is not going to fit perfectly in this data set, because as you can see, the regression line for this model is this green line over here. It's a different regression line. Then it means that the mean of the residuals in this testing data using the model from the training data, the mean is not going to be 0. It's going to be a value that is different than 0, because the fit of this model on this data, it's not perfect. But what we want is something that is pretty general, right? A model that it works with any data set, okay? It means, for example, that if we go to the field and we pick up this data set, if we go a different day and pick up a different data set, for example, a different seed, a seed number 10, then we use the model that we created, and the results that we are going to get are good. That's the goal, to see how efficient is the model and what is the best model for our data. Then we can create different training data and different testing data using the original data, right? Because here we separated the training and the testing data from the original data with a seed. For example, in this case, the seed is number 10. Then we can do the same analysis, but with a different seed. Then if we use a different seed, the training data, the samples are going to be different. And again, the testing data is going to be the difference between the original data and the training data. And we can be changing all the time this training data. Then we are going to have different testing data, and we can be doing the same all the time. And to see what is the model that fits the best in both cases, right? But we don't want to overfit this model on the data, because if we overfit this model on this data, when we pick up this model and bring to the testing data, the error, the residuals, are going to be so big because the model is not going to be fitting well on this data because it's overfit on this data, and this data, they have differences. But also we don't want to use a very simple model because a simple model is underfitting. We want a scenario that is something at the middle. We don't want something underfitting, but we don't want something overfitting. We want something that is well fit. We want the optimum model. Maybe all these terms now looks pretty complicated, but it's not that complicated. It's pretty easy and pretty straightforward. Okay, here we have another example at the bottom. This one is based in a GAM. This one, it was based in a linear model, and this one is based in a GAM. Okay, then we fit this model here on the training data, and then we take this model to put here and the testing data, and then we are evaluating the residuals using the model from the training data, because the model in this case for the testing data is the green line, but we are not going to use the green line. We are going to use the orange line, and the orange line is the model from the training data. However, in this exercise, we are not going to do analysis that is going to be univariate because our case is 3D, right? We have 3 dimensions. We have the X, the Y, and the elevation. That's the reason, because we are going to work with a GAM, but with multiple variables. In the GAM models, what we are doing is divided the data set in nuts, and each nut is going to be a section of the data set, and for each section what we are going to do is fit a type of spline. Okay, and that's what we can see over here. When we fit for a nuts, what we are going to have is a model like this one. But when we increase the number of nuts, we are going to have an object that is going to be more complex, because here in this one the data set has more sections, is divided in more sections. As we increase the number of nuts, the feature, the object is going to be more complex, because it's going to have the data set more divisions, and for each division we are going to fit a type of spline. Then at the end here is the same as explained as before, that we don't want a model that is underfit, and we don't want a model that is overfit. We want something at the middle. Remember that our goal is to predict this surface, right? And if we make something that is under predict, like this one, the results are going to be really bad, right? And if we have something that is over predict, what we're going to have is a model that is just adjusted to the data that we have. What happens if we take a different samples here, right? If we have a different seed and we have different samples, this model that is overfit is going to be also good for a different data samples. It's not, right? Because if it's overfit, the data, the model is specialized in that specific data sample. And if we change the data samples, the model is not going to fit well in that one, because it's very specialized. Then at the end we want something at the middle, and that model is going to be the deterministic model. Remember that at the top we have to add the stochastic model. The deterministic model is just the trend of the data. It's just the trend of this surface. Then for the detail of the surface, we are going to use the stochastic model. Then with the GAM, what we want is just to have the trend surface of the data. And again, what we want to have is a general model, a model that works not only with this data set, works with any data set from this location. You have to understand that these samples, try to be a representative of a total population of samples that is here, but we cannot take all the population. We take just a representative. And what we want is a model that works with any data set that is taken from this area, not only just this one. Then can you imagine how general has to be the model to work with any data set? And that's the model that we want to get. A model that works with all the data sets, not only just with this one. And in order to get that model, we are going to use the training data and the testing data. And these examples that you have over here are based on the testing data. I'm going to show you how you can take the model from the training data and put that one on the testing data and create these graphs. And then we are going to see later the interpretation of this data. Then we are going to see, first let's go to see this graph. Here we have the predicted error, that could be the root mean square error, and here we have the complexity of the model. Then as you can see, this one is the training data and this one is the testing data. Then at the beginning we have a big error, right? Because the model is underfit. And when we have a model that is underfit, like this one, if you compare this surface with this surface, you are going to see that there is big difference, right? Then the error for the residuals has to be bigger. And that's what you can see over here. It's bigger, not only for the training data, but also for the testing data. Has to be bigger, right? Then as we get more complexity on the model, the root mean square error is getting smaller and smaller and smaller, because the model is fitting better on the data. And when it happens, we have a better model. And that's what we can see over here. As we increase the complexity of the model, the root mean square error is smaller. Then the question now is when we are going to have the best model. And then we are going to have the best model when the error, the root mean square error associated with the testing data stabilize. Like this one, you can see stabilize, they go down, stabilize a little bit, and then go up. When this root mean square error stabilize, then we can assume that over there we have the best model. And what is the best model? The model that has this complexity over here. Then if we are in this range, we are underfitting. And if we are in this range, we are overfitting. We want the model that has this complexity. And this complexity is located here. When the root mean square error associated with the testing data using the model from the training data stabilize. When it stabilizes with the lowest value, it means that we have the best model. And what happened here with the training data? Well, with the training data, as we increase the complexity of the model fits better on this data, right? And as it fits better, we have less residuals. As we have less residuals, the root mean square error is smaller. But as we increase the fit on the training data, the results for the testing data are going to become worse, because here the model is overfitting on the training data. And then when we are using this model from the training data to fit the residuals, to fit the data on the testing, the residuals are going to get worse, because the model, it's very specialized just in this data. It's overfitting in this data. Then when it happens, we are on the overfitting area. The model over here with this complexity is not good because it's overfit. We want something over here. And that's what we are going to analyze, right? We are going to take the notch to see how complex is our model, the root mean square error associated with the training data, and the root mean square error associated with the testing data. Then we are going to plot all this information in a graph, and then we are going to analyze the graph in order to know what is the best model for our data. Then we are going to do this analysis for different training and testing data. But you have to know that for each training and testing data, we are working always with the same original data set. What we are changing is the samples that we have in the training and the testing data, just to have different models and just to compare the models in order to have a range based for the complexity of the model, right? What is the best range for the complexity of the model? Then after that, you know that we completed the deterministic model with the GAM, but now if we have residuals, we can do also an stochastic model, and that's what we are going to analyze at the end of the video, right? We are going to see if we have any spatial structure and how we can model that structure with a model, right? And what is the implications of this spatial autocorrelation of the data. Well, the overview for the job that we are going to do today is done, and now we are going to see a very short introduction about the generalized additive models before to start with the exercise. Then we know already how we can define the regression Kriging. We have a variable of interest that we want to predict, right? And this variable of interest is located at the space. Then the variable of interest is equal to two different terms. One is the deterministic term, that is the trend, and the other one is the stochastic term, and that's the probability. The stochastic term can be solved using the ordinary Kriging, and the deterministic term can be solved using different type of models. We already see the ordinary least squares, the generalized least squares, and today we are going to work with the generalized additive models, known as a GAM. Then we would like to know what is the difference between these models and this model. And I make here a very short definition, very general, but for me it works, right? First of all, what we can see is that the linear models and the general additive models are pretty similar, right? In both cases, we have the dependent variable that is equal to an intercept, that is the beta sub 0 in both cases, plus the independent variables, plus an error. Then in this case, we can say that the GAM, it's an extension of the linear models. But let's go to see closer what are the differences. Linear models or generalized linear models assume a fixed linear or some other parametric form of the relationship between the dependent variable and the independent variable. Then the relation between the dependent variable with the independent variables is linear. It means that if we make one change here at the independent variables, is going to affect with the same magnitude in the dependent variable. But the generalized additive models do not assume any linear relationship between the dependent variable and the independent variable. It means that the GAM can fit nonlinear relationships without any type of transformation. Sometimes when here we don't have a linear relation, right? We try to make some transformations in order to make this relation in linear, right? In this case, we don't need to do that one because we can fit the model in a very complex data set where there is no linear relation between the independent variables and the dependent variable. We no longer need that linear relation. And that is a big advantage of the GAM models because the GAM are pretty flexible. We can use the GAM in any type of data set. Another obvious difference is that in the linear models or generalized linear models, the dependent variable is a weighting sum of the independent variable or variables. As you can see, is this term over here. In GAM, this term is replaced by a sum of a smooth function, as you can see over here. And that function makes this model to be very flexible. As we already said previously, when we are using the GAN models, for each independent variable, we can divide the data set in NATs. And for one NAT to another NAT, we are going to fit a specific spline. And as we are adding more NATs, more complex is going to be the model, and better is going to be the fit on the data. And these allow us to make a very sophisticated models that fit really well on the data. Let's go to see an example, right? How the generalized additive models sometimes is an improvement compared with the linear models. Then let's go here, and we have this topography, and we take one section for this topography, right? One section from here to here, and what we are going to have is this section over here. Then we are going to move over here, and then we are going to put here some samples. Now it is obvious that if we have these samples, here we cannot fit a linear model, right? It doesn't make any sense. Well, we can try to fit a linear model, but it's not going to work well, right? We can do something like that, because here is where we have more data, and these data points over here are going to push this line maybe a little bit too up, and that one is going to be the linear model. But this model doesn't work well, right? To define this kind of shape of the data, right? Then we can try to fit a second order polynomial, right? In this case, it's going to be this one. This model is better than the first order, but again, it doesn't really fit really well on the data, right? Then we can try to do something more complex, right? We can try to fit a polynomial of 5 order. That is better than before, right? Because the polynomial is more complex and we can fit better the data. But when we are working with polynomials, we have a lot of problems, right? We can keep the linearity of the independent variables with the dependent variable, and the interpretation of the model is pretty simple. That's the good thing. But sometimes the polynomials doesn't fit well on the data. That's the problem. Sometimes we have a lot of problems with the extremes of the polynomials. Also, when working with polynomials of high order in a very area that is quite small, you know, for example, 500 meters by 500 meters, we have a lot of problems associated with the multicollinearity, right? That the different independent variables explain the same variability of the model, and it increases the variability of the model, and the variability is not real, right? And that's the problem associated with the multicollinearity, right? Because two independent variables are explaining the same variability of the model, and that's pretty common when we are working with polynomials in small areas. Then, in order to avoid the multicollinearity, we have to work with polynomials that are orthogonal. But in order to create orthogonal polynomials when we are working with surface, when we are working with 3 dimensions, is very, very complicated. And to create that kind of features, it's very, very difficult when the degree of the polynomial is so high. Then the best option when we have let me remove this one. When we have a very complex data set that is showing a no-linear relationship between the independent variable and the dependent variable, the best option is to use a generalized additive model, because the splines can fit on the data really well, and it doesn't give us problems related with the multicollinearity. You can see here an example, right? Then here we have this one is the real surface, right? But when we create the model, you can see here how complex could be the deterministic model that represents really well the reality, right? As you can see over here, this image and the high degree of splines makes the deterministic model pretty similar to the reality. Before to conclude this section of the video, I would like to talk a little bit about the assumptions related with the GAN models. And the assumptions that we have is the same that we was using when working with linear models or generalized linear models. Then for the GAN, we don't need to cover the linearity. Then we can break this assumption because the model is very flexible and can be adapted to non-linear relationship between the independent variable and the dependent variable. Then for the assumption of normality for the residuals, we need to cover that assumption. Also, we need to cover the assumption related with the homostochasticity. The error for the variance in the residuals has to be constant. And also we need to cover the assumption related with the independent of the residuals. Then we don't want to have autocorrelation on the residuals. But we are going to see that this last assumption, maybe it's a little bit flexible, because when we are fitting GAN models on the data, as the fitting is really good and very close to the data, we are going to have a minimum residuals autocorrelated. And with that minimum residuals, maybe we can apply ordinary Kriging, because the autocorrelation is not really big, right? We have a very small autocorrelation that is close to maybe to the pure Nager effect. But if we have pure Nager effect, we cannot apply a stochastic model. Then sometimes maybe it is interesting to have a little bit of autocorrelation in order to apply ordinary Kriging. Then as a summary, we can say that for the ordinary least squares, we have to cover the assumption of linearity, the assumption of normal distribution of the residuals, the assumption of constant variance for the residuals, and also the no autocorrelation for the residuals. Then if we have heterostochasticity and we have a spatial autocorrelation, then we can use the generalized least squares. Here we have to cover the assumption related with the linearity and also the assumption related with the normal distribution of the residuals. But what happens if we cannot cover the assumption of the linearity? Then we can use the generalized additive models. In the generalized additive models, we don't need to cover the assumption of the linearity of the independent variable with the dependent variable. But we have to cover the rest of the assumptions. The one related with the normal distribution of the residuals, the one related with the homostochasticity of the variance, and also the one related with the no autocorrelation. But for this last one, we can say that if we have just a small autocorrelation, that is not going to be that bad, okay? Because it's going to be a very small autocorrelation, and maybe we can apply ordinary Kriging on that spatial autocorrelation. Now the next step is to generate the data set. First, let's go to load the digital elevation model on QGIS. Then select this option, select the raster here, and I have the digital elevation model in this folder in the DEM. Double click, open, add. I want this reference coordinate systems. This one is good. Okay. And apply and okay. Then I added 2 times, remove. Okay. And now I'm going to edit this layer a little bit with the different colors. this one is good. Then equal intervals, and it's going to be 10 classes. Apply and OK. If you are wondering how I get this digital elevation model from LiDAR data, I recommend you to follow the video tutorials on the YouTube channel. Here I have these 3 lessons are related with digital elevation models, and this lesson at the middle is how you can create a digital elevation model using LiDAR data with the last tools software. Also, at the GeoRGB community website, you have this course that is related with that topic, with the same lessons, but here you can download the files and etc. Now, the next step is to cut this raster. Then I'm going to create a mask layer. Then it's going to be layer, create new layer, and it's going to be a shape file. Then we are going to save this shape file at the folder related to shape files. Let me see where I save this one here, overfitting, and it's going to be this folder over here, and it's going to be perimeter. Then save, and I want the geometry polygon, and I want the reference coordinate systems the same as this one, 26, 9, 11. It's going to be 26, 9, 11. It's going to be this one, select and OK. And that's good, OK. Then we are going to press the pencil to edit this layer. Then right click on the mouse on this area and select Shape Digitalizing Toolbar. Then we can select the square here from Extends, and then we are going to select the area. And we want to create here a rectangle that is going to be about this one, that is 500 by 500 approximately. Then left click, select an ID that is going to be number 1, OK. And now we can close the pencil here, save. And if we measure the distance, that is in meters, we have that it covering an area about, sorry, not this one, close, from here to here, as you can see, is 562 meters, and from here to here is 532 meters, okay? Then close. Now we can use this shape file to cut the raster. To do that one, go to raster, extraction, clip raster by mask layer. Select the input is going to be the DEM. The mask layer is going to be the perimeter, the layer that we created. And we want to save this new raster file, that is the DEM cut, in this folder at the overfitting, in DEM with the same name, but I'm going to add here cut. Then save, and then we can run. And now we can close, and now we have 2 DEMs. We have this one that we are not going to use more, and the new one. Then we can edit again the color, properties, go here, pseudo color. This one is good, same as before, 10. Apply and OK. Now we can visualize this digital elevation model in 3D. Then we can use this plugin. If you don't have this plugin, just go to plugins, manage plugins, be connected on internet. Then that one is QGIS 2T, and is this plugin over here. Just select the plugin and install. Then I have the plugin already installed. Then I'm going to run this plugin. Then select this one here. And then we can take this one at the moment, and we are going to work with this one. Go to properties, Then here I put these values to the maximum, also the image width to the maximum, and here I'm going to select clip and going to select the perimeter, apply, and OK. Now here we have the model. As you can see, the topography is really good. The resolution is really good. We can see a lot of details of this topography, right? And it is supposed to be a river over here, I believe. Okay, now we can close and extract the samples from this topography. Then we have to go to vector creation here and select random points in polygon. Double click. Here the input layer is going to be the perimeter. The number of samples is going to be 200. The minimum distance between the samples is going to be 10 meters. And at the moment we are going to select the random seed that is going to be the number 1. Then we can run this one, close. And the next step is to check that all the points are inside the raster, because if we have any sample that is outside of the raster, we are going to have a null value. Then we want to verify that all the points are inside the raster file. At the moment, everything looks good. Okay, then we are not going to have null values with this seed. Then the next step is to download a plugin. The name of the plugin is Point Sampling Tool. Then go here. It's going to be Point Sampling Tool. Is this one over here. Then we can install this plugin. And what we are going to do with this plugin is to extract the values from the raster where we have a point on the shapefile. The shapefile is this one, where we have one point, that is the sample. We are going to extract the elevation just in that in the same location where the point is on the raster. Okay. Then to do that one, we can press this option over here, select the raster here, and save the final result in a folder. This one, shapefile, and we are going to save as a shapefile, and it's going to be sampling. Then save, and now we can run. Okay. Now the file is already generated. Okay. No, we don't want to do again. Then close. And then we can open the attribute table. And as you can see, now we have the elevation for the 200 points. Now the next step is to add the coordinates, the X and the Y. Then press the pencil over here to edit this layer. Select the open field calculator. Then we are going to create a new field that is going to be the X coordinate, and we want a decimal real number. Then here we are going to add the dollar symbol plus the X, and we are going to use this value over here. Double click, and with this one, what we are going to add is the X coordinate. Okay, we have already the X coordinate, and now we are going to add the Y coordinate. Then Y, we are doing the same, selecting decimal number, and we can go also here to geometry and look for that dollar symbol with the Y. Is this one over here. Double click, and if we press show help, it's going to provide the information about this parameter, right? Then OK. And now we have already the Y coordinate. Now we can close the attribute table, save, and close. And now we no longer need this one. Then we can remove this layer. Okay. Now what we want is to export this file as a CSV. Then export, save feature as. Then here select the format you want, is this one. select a folder that is going to be overfitting, dataset, samples, then save. This one doesn't matter, and OK. And now we can open that spreadsheet. Then go here, overfitting, dataset, and it's this one. Double click to open, and now we can edit this spreadsheet. Okay, open as a copy. Now I want to move this column, then cut, and I'm going to paste over here, paste, and I'm going to change the name for elevation. Also, I'm going to remove this one over here. I'm going to select the 3 columns, format cells, and I want to be number with 2 decimals. OK, and that's it. Then I'm going to put everything at the middle, and now we can save this data set. Field, save as. We want to the format CSV. We are going to save at the data set over here as a, not this one, sorry, number 3, overfitting, data set, samples, final. And save and close. Keep the current format, and now we can open this spreadsheet with Art Studio. Double click to open Art Studio. Now I'm going to paste all the things I did, and I'm going to start from the beginning. In this lesson, what we are going to do is overfitting, testing, and training for the generalized additive models. Then if you don't have any of these packages, you can use the install package to install any of these ones, but I'm going to run all the libraries. Then we're going to use all of them, even more that you are going to see later, at different packages. Also, I'm going to use the name B for the data set. As you can see, we have 200 observations with 3 variables. That is the X, Y, and the elevation of the terrain, right? As we can see over here. Then I'm going to make a backup with the name B2 if we need to make any transformation with the data set. We can use the backup. Now I added this comment over here just to recommend to watch one video tutorial about GAM models in YouTube. You have the link over here. This video tutorial is about 3 hours, and it is an introduction about GAM models, and it is really good. Then you can watch this one if you want to go deeper on the understanding of GAM models, okay? Now the next step is to load the library MGCV. This library is for the generalized additive models. Then I already installed the package, then I have just to run the library. Now let's go to start with a real example, and let's see what kind of information we have to add inside of a GAM object. First, we are going to work with just one variable that in this case is going to be the X coordinate. Then I'm going to call this object as a GAM model, and the script that we are going to use is GAM. As you can see in this script, the information that we added inside is pretty similar as the information that we was adding at the linear models. Then first, we are going to put here the dependent variable, and we are going to say that this dependent variable is depending on the X coordinate. And this X coordinate is inside of a smooth function. Also, we have to tell the script where is located the data set. In this case is B, is this data set over here, and also the method that we are going to use. In this case, we are going to use the restricted maximum likelihood. Also, I added here the term BS equal to TP, indicating what type of spline I want for this object. As you can see, we can use different types of spline, changing this name. For example, we can use also the cubic regression splines if we add CR. But the most commons are this one, the thin plate, and also the cubic regression. But here you have an explanation when to use the other ones. We are not going to go deeper in this topic, and we are going to use at the moment the one that appears by default if we don't specify anything, okay? Then if we remove this option over here, the one that we are going to use is the thin plate, okay? But I put here just to make emphasis on the type of spline that I'm using. Now we can run this object and see the summary to see what kind of information this object can provide us. We can maximize these windows and see what information we have. It's saying that we are working with the familiar Gaussian. Then we have a normal distribution. This one is the link function identity. This one is the formula that we are using. Here we have the intersect for the beta sub 0, as the same as we was talking when we was working with linear models. Then also here the new thing is the effective degrees of freedom, okay? When we was working with linear models, we have the degrees of freedom associated with the number of variables that we was using in the model, right? Here is a little bit different, and what we have is the effective degrees of freedom that we are going to be talking later about this parameter. And also we have here how much the deviance is explained by the model, and in this case is a 53.4%, and the number of samples and the method that we are using. This one is the one we specify at the model over here. Now we can see also the summary related with the residuals. As you can see, the mean value is 0, and the minimum is minus 53, and the maximum is 34. And here we have the first quantile and the third quantile. And also we can make a histogram to see how the residuals are distributed. Then we can use this package to create the graph. Then if you don't have the library, just install the package. I did already, and then I can run the library. Then the next thing that we are going to do is to use this script to create this object with this model. We need to create this object in order to plot the graph with this library. Then we are going to run this object, and now we are going to print the graph using this package. The how works the graph, it's pretty similar to the ggplot, okay? We are adding things to the graph. And now we can make a zoom. Then in this graph, we have the data set, that is the black dots. Also, we have the model, that is this black line. And here we have the x coordinates. And here what we have is the degrees of freedom. As you can see, for this smooth function, the degrees of freedom is 2. And as we have 2 degrees of freedom, the model cannot be very complex. And in this case, it's almost just a straight line. Now, let's go a little bit further on the analysis of this model. Then what we are going to run is this script, the GAM check, okay? And we're going to check the GAM for this model, the one that we created, okay? Then we can run this object and see the information. This script provide 4 different graphs. This one, this one, this one, and this one. But at the moment, let's go to stop over here and see the information over here. Then here it's saying that we have 9 nuts, and we have 2 effective degrees of freedom. And the important thing here is to verify this condition, that this value has to be bigger than 1 in order to have a valid model. And in this case is good, because this number is bigger than 1, then we have a valid model. But the interesting thing is, as we said previously, when we introduced the GAN models, we said that the data set is divided in nuts. And for each nut that we are using, we are going to have a section of the data set. And for that section of the data set, we are going to fit an spline. And then if we have, for example, 10 nuts, we are going to have 9 sections of the data set. And for each section, we are going to fit a spline. And for each of these splines, that they are smooth functions, we are going to have a coefficient. Then if we have 10 nuts, we are going to have 10 coefficients. And that's what we are going to see over here, coefficients of this model, right? If we run this one, we can see that we have 10 nuts. I mean 10 coefficients. The first coefficient is for the intersect, and the rest of the coefficients are associated with the number of splines we assign to that model. And by default is 10. When we didn't add any information here at the smooth function, it takes the number of nuts equal to 10, okay? And that's the reason, because when we are checking, we can see here number 9. 9 is 9 nuts, it's for the functions, and 1 nut is for the intersect. And that's what we can see over here, in all this line over here. Then how it works? Okay, we have this model, and this model comes from a data set that has been divided in 9 different sections with 10 nuts. Then for each nut we have 1 coefficient, and the first coefficient is the intersect, and the rest of the coefficients are associated for each section of the data set that we divided. Then in each section we have 1 spline with the coefficient associated. Then we can say that in this model that looks like just a straight line has 9 different splines. But when we are checking the degrees of freedom, we have just 2 degrees of freedom. Remember that when we was working with linear models, the number of degrees of freedom that we have is the same as the number of variables that we was using, right? Remember that for each variable, we have 1 coefficient, beta, right? And in this case, what's going on, right? Because we have 9 different sections with 9 different splines, and each spline has his own coefficient, but we have just 2 degrees of freedom. And that is because the model is fit on the data by the software, by the algorithm, automatically, and the software decide what is the best model according to this data. And the best model according to this data is this model. We can specify the number of nuts we want, but the model is taking in consideration that you add too much nuts in this model, because the model is taking in consideration that with 2 degrees of freedom, it's enough to make the representation of this model on this data. Then you can add the number of nuts you want. You can add 100 nuts, but then the software is going to fit the model automatically. That is going to be the best fit, and is going to take in consideration how many degrees is going to be according to the model the software fit on the data. It's like the equivalent, right? You put 10 nuts, But the software is saying, no, that's too much. Because with 2 degrees of freedom, that it's enough. You have a good model. And how is doing the software that one, right? It's taking in consideration an extra parameter that is known as a lambda. The lambda parameter is how complex is the model, right? Because you can take 10 nuts and make a very complex model. But you can take 10 nuts like this one and make a very simple model. And now we are going to see another example about how complex we can make the model, okay? Then in order to do that one, we are going to make some modifications on the initial object. And in this case, we are going to add the term SP. SP is the lambda parameter, okay? And as smaller is the lambda parameter, more complex is going to be the model, okay? In this case, we are going to add 0.01, and we are going to add also the K, that is the nuts, that is going to be equal to 10. We know already that the 10 value is the value that appears by default, okay? But in this case, we want to put the value just to indicate exactly what we are doing, okay? Then we can run this model again and see what is the final result for the graph. Then we can see this one, run this one. This one is going to be the model, and as you can see now, the model is more complex, okay? And now we have more degrees of freedom. And if we check that one here, we are going to see that now the degrees of freedom, the effective degrees of freedom, is higher. Before it was 2, now it's 7, okay? And also another important thing, that this value, the effective degrees of freedom, always has to be smaller than this value over here, this K, okay? And if we see the model, let me show you the model. Sorry, this one over here. Let's go to make this screen bigger. Now we can see that the model is more weakly. It's more complex. But the question is this model better than the one I showed you before? And the answer is not. Because here we forced to fit this model on the data. Because the model is fit on the data automatically, okay? We don't have to be worried about the lambda parameter. The lambda parameter is selected by the algorithm. We don't have to specify anything, okay? We have to specify just the number of nuts, but not the lambda parameter. The lambda parameter is specified by the software. The software decides what is the best lambda according to your data, and then provides the best fit for the data, okay? And we don't have to be worried about that one. Then this model is not better than the one I showed you at the beginning, because the one I showed you at the beginning, it was the one that the software decided to fit, right? And that's the best fit. The best fit according to this model, okay? And we are using this model because this model is numerically more stable, okay? If you don't specify here any model, the model that appears by default is going to be the generalized cross-validation, known as a GCV, but the most recommended one is the restricted maximum likelihood. I'm not going to go deeper in this concept because I don't have the knowledge, and also it's a little bit complicated, but that one is the one is recommended. Then if you want to do some GAN models and you don't have too much experience, just use this model, okay? And again, don't worry about the lambda. The lambda is selected by the software. Just check the number of nuts. Then if the model is no good because this value is smaller than 1, then it indicates that you have to increase the number of nuts, okay? But if you put here, for example, 100 nuts, we can do that one. We can take this one out. and we can increase the number of nuts to 100, you are going to see that nothing changed on the final result. Let me show you. Then we can run this one again from the beginning. Let's go to run everything, print the graph, and as you can see now we add 100 nuts, but the degrees of freedom is still the same, because that's the model that fits the best on the data according to the algorithm, right? Then even if we check the model with the GAM check, you are going to see that now we have 99K, but we have the same degrees of freedom. There is no improvement, right? The only thing is happening here is not bad to add 99 degrees of freedom. The problem is that it's going to be computational. It's going to be more cost for the computer, right, to process all the things. But nothing changed in this case. Even you are going to have a lot of coefficients, but the model is still the same, right? As you can see, the model is the same. Now, to finalize this section, I would like to introduce some terminology and make a small summary, right? Then we have this function, and this function is our model. And we have to understand that this function is composed by simple functions, right? As we said, in this case, we have 100 nuts, and 100 nuts represents 99 different sections in our data set. And for each of these sections, we fit an spline, okay? Then we can say that this function is composed by simple functions, and these simple functions are known as basis functions, and the set of basis functions is the basis, okay? And the basis is the model, is our model, right? Is the final function. Also, for each of these simple functions that compose our basis, we have, for each of them, we have one beta coefficient. Then in this case, as we have 99 different sections, we have 99 splines, and for each spline we have one coefficient, and that's what we can see over here. And always the first coefficient is going to be the intersect, as you can see over here. Then we can add the number of nuts that we want. It doesn't matter, right? Because the software is going to fit the model automatically. Then the software is going to provide us what the software thinks is the effective degrees of freedom that we have in our model. And in this case is 2, right? Then the software is saying, okay, you can put the number of nuts that you want, but the equivalent that I decided to assign to your model is this one. And that's the value that we have to take in consideration, right? Now let's go to work with 3D, okay? Now we are going to add the X coordinate, the Y coordinate, plus the elevation. Now we are working then in 3 dimensions. Then I'm going to load this library to have a 3D interpretation of our data set. Is this one? Here we have the X coordinate, here we have the Y coordinate, and here we have the elevation. And with this graph, we can see how our data is distributed at the space, right? It's something interesting, right? To see what is the trend related with our data. We can see that our data is doing something like that, right? We know already because we saw the real 3D model associated with this data set, right? But it's interesting to see how the trend looks in 3 dimensions. Now we can close this one, and we are going to run this model. Now we are going to put this name to this object that is going to become model number 1. We are using the same script as before, and now the elevation is depending on the x and y. And here in this case we added 50 nuts, and we can remove this one because the thin plane is going to be the one by default. We don't need to specify that one. We have to specify where the data is located. In this case, it's at the dataset B. And also we have to specify the model, right? Because by default, it's not this model. It's the generalized cross-validation. And we don't want to use that one. We want to use the restricted maximum likelihood. Then now we can run this script. Let me start from here. And I make this note over here, but that one is not good because it's sometimes the default number of nuts, k, right? It's not good. Then always we have to check if we have enough degrees of freedom, right? Then now we can see the summary. I'm going to run this one. And I can make this one bigger. The same as before, right? We have the family that we are using, the link function, the formula, the value for the intersect, the degrees of freedom, in this case the effective degrees of freedom, and how much the deviance is explained by the model. As you can see in this case, it's really high. It's 99.6. That's a really high value, right? Then the next thing that we can see is the summary for the residuals. Remember that in this case, the model is with 2 variables, right? It's multivariable, right? Then we can see the summary for the residuals. We have the mean that is 0, the median that is very close to 0. That is very interesting to make sure that your histogram is symmetric, right? And it's the data is normally distributed. And also here you can see the minimum value, the maximum value. They are pretty equivalent, right? And the first quantile and the third quantile. Now we can plot the histogram related with the residuals for that model, and as you can see over here, it's normally distributed. And now we can use this script to visualize our model in 3 dimensions. Okay, you can change also the angle to have a different view. Then we can run this one, and here is our model. No, in this case it's a 3D model. And now we can check the model. And in this case, as you can see, the value is smaller than 1, right? It indicates that we have to increase the degrees of freedom in this case, because it's not good enough. We want this value to be bigger than 1 or very, very close to 1, okay? Also, as I said previously, when we are doing the GAN check, we get 4 different graphs, right? The first graph is the response versus the fitted values. We have the response here and we have the fitted values here. And what we want is to have a line like this one. The data set is making this kind of line. This one is indicating that we have a good model, right? Then the other one is indicating with the residuals of the histograms. What we need here is to have a normal distribution of the residuals. Then the next one is associated with the homoscedasticity, right? The constant error for the variance. Here in this graph looks pretty good, right? And the last graph is related with the QQ plot with the residuals, right? What we want is the black dots to be on the line, right? And that one is going to indicate that we have normal distribution on the data. One interesting thing in this case is that the effective degrees of freedom is taking almost all the nuts. As you can see, the numbers are pretty close, right? And that is indicating that we need more degrees of freedom to be added over here to fit the model on the data. And if we add a little bit more, we are going to be close to 1. And that's the goal, right? We want to remove this asterisk from here and have here a value that is close to 1 or bigger than 1. Now let's go to see what happened. For example, if we add here a number 4, right? In this case, the number of nuts, it's pretty small. Then in this case, we are going to divide all the data set just in 3 sections, right? And with 3 sections, we are going to feed the splines and we are going to see what model is going to create. We know it's going to be a bad model because with 50, it's still not good, right? But we are going to see how bad is the model. Then we are going to run this one. As you can see now, the model can explain 75% of the deviance, right? Then the summary for the residuals. We have these values. As you can see now, it's pretty asymmetric, okay? And we can see the histogram now, that you can see all these values over here, right? Then we can make the 3D interpretation of the model. And as you can see now, almost is a flat plane because we don't have too much nuts, you know, to explain the variability of the model. And now also we can check the GAM. And we are going to see that we added 4 nuts, and most of the nuts are absorbed by the model, right? Because the model needs more degrees of freedom and it's taking all the possible degrees of freedom that can provide the number of nuts, okay? And in this case, the maximum can be 3. And remember, as I said previously, this number can be never bigger than this number, right? And it's taking the maximum, that is close to 3. And now let's go to see what happens if we add, for example, 60, right? Then we can run the model again. And also, as you can see, for the 4 nuts, we are seeing here that the graph is not good, right? Because what we want is to have just a straight line that is making an angle of 45 degrees, right? Here in this graph, we can see that the model is not good. And also for the histogram, for the homoscedasticity, you can see that it's not good also. For the last one is the QQ plot. Also, the dots are not good because they are very out of the red line. But now let's see what happened with the 60 nuts. Then we can run this one. We can see the summary. Here we have 56 degrees of freedom, effective degrees of freedom. And now we can explain 99.7 of the deviance with this model. Then we can see the histogram for the residuals. First, the values associated with the residuals, the minimum, the maximum, the first quantile, the third quantile, and the median and the mean. As you can see, this histogram is going to be pretty symmetric, right? As you can see on this image. And now we can make a 3D interpretation of the model. This one is the 3D interpretation, and now we can check the model. And in this case, the model is good because this value is higher than 1. And now the software is taking the effective degrees it needs from the number of nuts. But it doesn't, this number is not close to this number, right? It means that even we have some room to put less nuts in this model. Also, we can check this graph that is making a straight line with 45 degrees. This data representation is good for the model. Also, the residuals are normally distributed. That one is good. For the homoscedasticity, we have a constant variance. That is also good. And the QQ plot is not that bad. because the black dots are close to the red line. That is the ideal scenario for the normal distribution of the residuals. Then at the end, what we are going to say is that the best model is the model that shows less complexity, right? But it's going to be an interval, a range, right? We can say, for example, from 55 nuts to 65 nuts, we have good results, right? But we are not sure what is going to be the best model because it is a range. Then what we can do if we have a big data set is to train the data, right? We can divide the original data in training and testing. And in this way, we can have a better approximation about what is the best model, right? When our data set is not really big, we have to be limited to use this information, right? But when we have a big data set, we can do something different in order to have a better approximation. We can use this information, but also we can use the information that provides the training and the testing data, and that's what we are going to do now. Then we are going to divide the original data set that has 200 observations, 200 samples, into different sub data sets. One is going to be the training, and the training is going to have 150 samples, and the other one is going to be the testing, and the testing is going to have 50 samples, okay? Then we can divide the original data set in a different way, right? This one is one way, but in this case we are going to use this way, okay? With this way we can add a seed, okay? And the seed is really important because as we are changing the number of the seed, we are going to have a different training data. Then when we have a different training data, we are going to have a different testing data, okay? Because the training, the testing data is the difference of the original data set less the samples from the training data, okay? Then as we are changing this one, that one also is going to change. And for each number of the seed, we are going to have a different training data, okay? In this case, we can start, for example, with the number 3 and establish this one as a seed. I'm going to run all these ones from here. And now what we are saying is that the samples, we are going to create an object that is samples, and this object, it comes from the B data set, and what we want to use is the elevation parameter, okay? Then we want with this parameter to create a partition, and this partition is going to be the 75% of the data set, okay? And this 75% is going to be the training, okay? And then the rest, the 0.25%, is going to be the testing, okay? Then we can run this one. And now the training and the testing. And as you can see, now we have two different new data sets. One is with 152 observations and the other one is 48 observations. Okay, it's not exactly the 75 and the 25%, but it's close enough, okay? Before to start with the analysis of the generalized additive models with the training and testing data, I'm going to do the same, but with a simple model that in this case is going to be a linear model, okay? Then we are going to use just one variable. We are going to say that the independent variable, I mean the dependent variable, that is the elevation, depends on the x coordinate, okay? And this one is a simple linear model. Then I'm going to call this one as a model original, and I'm going to run this model. Then we can see the summary of this model, that we have just 2 degrees of freedom, but the model in total has 198 degrees of freedom, okay? Then we have the intercept. We have 2 beta coefficients in this case. One is associated with the intersect, and the other one is associated with the independent variable x coordinate, okay? And this model can explain 52% of the variability of the model. Then we can plot the model with the ggplot, and we can see how is this model. This one is the information that we have. This one is the original data. Here we have the 200 observations, and here we fit the linear model associated with the first order trend surface. Okay, is this one. As you can see here, we use the original data set. Now we are going to do the same, but now what we are going to use is before to run this one, I would like to talk about this one. We are going to use the training data, okay? It's the same, but with the training data, with the 152 samples. Then I'm going to select this model, and I'm going to run this one. We can see a summary is more or less the same as before, but now the degrees of freedom for the model, it's a little bit smaller, right? Because we have less samples. Then we can also run this script to see the plot. Then the graph is going to be this one. Is more or less the same as before, but now we are working with the training data, and this one is the model associated with the linear model for the first order trend surface. And now we are going to do the same, but for the testing, okay? Now we are using the testing data. Then we can run this model. We can see the summary. Now even we have less degrees of freedom for the model because we have less samples, right? And now the model can explain less variance of the model because we have less samples, okay? Then again, we can plot this one and see the results over here. This is the testing data. We have just 48 samples, and in this data we fit a model. And this model is a linear one with the first order trend surface. Now what we can do is plot all the graphs together with this script over here. And let's make some zoom over here to see the three graphs together. And now we are not going to work with the original data. We are going to work just with the training data and the testing data. And what we are going to do is take this model that we get from the training data, and we are going to use this model on the testing data. And with this model on the testing data, we are going to evaluate the residuals. We are not going to use the model that we get from the testing data. This model we are not going to use. The model that we are going to use is the model from the training data on the testing data to see how good is this model on a different data set but from the same location, and that's the goal. Now we can see the same example, but in this case we are using the GAM, okay? Then we are going to use just one variable that is going to be the X variable, but we are using a smooth function, okay? Then we can run this model. Then let's go to create the object, and now we can plot the graph. Now I'm going to show you. This one is for the original data, for the 200 samples. Then when we fit the model on the 200 samples, what we are going to have is this model over here. Now we are going to do the same, but just using the training data, okay? Now we have just 152 samples. It's going to be the same, but with the training data. Then we can run this one. Let's to create the object. Now we can create the graph and plot the graph. And now what we have is the same, but with 152 samples. And now the model is this one. And as you can see now, the degrees of freedom, it's a little bit less. Now we are going to do the same, but with the training data, with the testing data, okay? Then we create the model, the object, then we create the graph, and now we can plot the graph. And as you can see, in this case, we have just 48 samples, and for these 48 samples, we have just 1 degree of freedom that is known as an effective degree of freedom, okay? And this one is the model. Then I try to put this graph and this graph together, but I couldn't use this script, the grid arrange. Then what I did, I copied the graphs with this option, copy in a clipboard, and I paste over here to have the training data and the testing data for the GAN model, okay? Then again, what we are going to do is to take the model from the training data. We are going to place this model over here, and we are going to evaluate the residuals using this model on the testing data, okay? We are going to place this model over here, and we are going to calculate the residuals. We are not going to use this model, okay? We are going to use the testing data with the model from the training data. Then we are going to use this model. But we are not going to do this analysis in 2 dimensions. Here we have the X, and here we have the elevation. We are going to do in 3 dimensions. We are going to use the explicative variables X and Y, that they are the coordinates, and also for the dependent variable, we are going to use the elevation. And that's the next things that we are going to do. Then first, we are going to create a model with 4 nuts. Remember that what we want to do is create several models with different complexity. Then what we are going to do is increasing the number of nuts. The goal is to create, let me show you the other graph, a graphical representation of the error associated with the complexity of the model, okay? Remember that we was talking about this topic at the introduction of the video, and we want to create a graphic like that, right? Where we have the training data and also the testing data, and then we are increasing the complexity of the model, and we are calculating the root mean square error for each of these models. Then where the testing data stabilize the root mean square error with the lowest values, then is going to be the area where we have the best model, the range where we have the best model, and this model is going to be with this complexity over here, and that's what we are going to do now. Remember that here we are evaluating the residuals with the training data and the model associated with this data set. And here we are evaluating the residuals using the testing data with the model from the training data, okay? Now we can go to R and start with the 4 nuts. We know that 4 nuts are not going to be good, but we want to have the information in order to create the graphical representation, okay? Then we are going to run this one. We are going to call that one models multivariate, because we are using the GAN model for 2 variables, that is the X and the Y. Also, we are going to add the number of nuts. We are going to say that we are using the thin plate, but as you know already, we don't have to use this argument, because that's the explain that the software used by default. Then what we are going to do is use the data training with this method, okay? Then we can run this script. And with the next script, what we are going to do is adding the predicted and residual values to the testing data frame using the model from the training data. How we can do that one? With this script. We are going to see that this new variable is equal to this script over here. What we are using here, the model from the training data, okay? We are using this model, and this model is using the training data, as you can see over here. And we are saying, okay, we want to do this one using this object, that is this object over here, but with the new data. In this case, the new data is the testing, okay? Then we can run this script. Now we add in this data frame, we are going to add a new field that is going to be predicted, that is equal to this value. This value is this value over here. Then, as you can see, now the testing data has just 3 variables. Now we are going to add one extra variable that is going to be the predicted values. The predicted values, remember that it is the model, okay? It's the values associated with the model. Then we can run this one. And as you can see, now we have 4 variables. Then we can open this data frame. Sorry. And as you can see, now we have the X, the Y, the elevation, and the predicted values. The predicted values of the model from the training data, okay? That's the important thing. And now we are going to add the residual values, and the residual values is going to be equal to the elevation minus the predicted values, okay? We calculated the predicted values over here. And then we are going to add a new field on the data frame, on this data frame, on the testing, that is going to be the residuals, okay? Then we can run this line, run this one, and now we can see the data frame again. The testing data, the testing, now we have one new field that is the residual values. And these residual values are from the testing data using the model from the training data. I know I'm very repetitive, but I want to make sure that everything is clear, okay? Then the next thing is adding a quality control just to verify that the predicted values plus the residual values are going to be equal to the elevation, okay? Now we can see that the quality control is, for example, for the first value, the elevation is 580.51, and when we plus this value, we get the same value. It is indicating that the model, it is okay, okay? There is no something wrong over here. We can check several values. For example, this one, it's also good. Now, the next step is calculate several parameters, but first, let me save the project, save, and I'm going to save this folder, overfitting, our project here, and it's going to be GAM. Save. Okay, and now what we are going to do now is adding the predicted and residual values to the training data set based on its own model. Okay, we are going to do the same, but for the training data, as we did here for the testing data, but we are going to do the same for the training data. Then we can run all these scripts. It's the same as before, but using the training. And now if we go here to the training, we now can see that we have 6 variables. If we open the table, you are going to see that for this data set, now we have also the predicted and the residuals. Remember that we want to have the residuals for both models because we are going to calculate the root mean square error for each of these models in order to create this graph. This graph over here. Then we can go to the scripts And now we can calculate several parameters. The first parameter that we are going to calculate is the cross-validation correlation, okay? This parameter is the correlation between the observed and the fitted values for the testing, okay? We are working now with the testing. We need to calculate this value in order to calculate the next parameter. Then we can run this value. And we can see also the amount. As you can see, we have 0.75, and these are really high correlation, okay, between the elevation and the X and Y coordinates. Even the model doesn't fit really well because we have just 4 nuts. The correlation is still good, okay? Then also we can calculate the R squared value, again for the testing, and see what is the value for the R squared. And in this case is 0.56. It is indicating that this model, the model that we creating for the testing data, is explaining 56% of the variability of the model. Then the next parameter that we are going to calculate is the shrinkage. And this parameter is the difference between the R squared from the training data and from the testing data. Then we can run this value over here, and now we can see the amount. As this value is close to 0, is indicating that the model that we fit on the training data and the testing data is explaining the same variance in both models, right? Because when we make the difference, if that is pretty close to 0, it's indicating that in both models, the model explains the same variability. And when this value is farther from 0, it's indicating the differences between the models, right? Then we fit the model from the training data on the testing data, and if they explain a different amount of variance, it is indicating that the model from the training data that fitted on the testing data is not really good, right? Because they are pretty different. Then what we want also is to have this value always close to 0, right? At the end, what we want is to have this parameter with a value that represents less than 10%, okay? With less than 10%, we can say that we have a really good value. And for a value that is higher than 50%, it is not good, okay? Then in this case, as we have 0.01, we can say that we have 1%, okay? In this case, it's pretty similar, right? The model fitting in both data sets are explaining, in both cases, the same amount of variance. Now we can plot the residuals against the fitted values for the testing data, okay? As you can see, this graph is showing an invalid model where we have a trend on the data, right? And this model is not going to be good, but we are not going to use this model. What we are going to get from this model is just the values associated with the root mean square error for the testing data and for the training data, for the residuals, right? But we are not going to use this model. Then we are going to now calculate another different parameters. Then it's going to be the mean value for the residual for the testing data. And what we can see is this value, it's not 0, right? And we have to understand that when we are fitting a model using the GAM, the residuals are calculated based on the ordinary least squares. And the ordinary least squares minimize the distance from the model to the observed value in order to have the minimum residual. And when we are taking the mean value for the training data, in that case, the residuals are going to have a mean value of 0, because in that case, we make the perfect fit according to the ordinary least squares, and we minimize the value associated with the residuals, right? But when we take that model and we place that model on the testing data, we cannot minimize the residual values, because that model is not from that data set. It comes from a different data set, and that's the reason, because the mean value for the residuals from the testing data, it's not 0. But the ideal scenario is to have a value that is close to 0. Then we have to take in consideration also what mean value we have for the residuals, okay? And another important thing is related with the standard deviation, okay? We want to have this value also close to 0, because as this value is close to 0, is indicating that the residuals are less spread. They are most close to the 0 value, and we want that one, right? We want to have the maximum residuals to be close to 0. In addition, if we have a standard deviation that is similar to the training data, it is indicating that the model works well also on the testing data, and that's the comment I added here, right? The ideal scenario is the mean to be 0 or close to 0, but never is going to be 0, because we cannot minimize the residual values, because the model that we are using, it doesn't come from that data set, right? And also what we want is the standard deviation similar to the standard deviation that we have on the training data. Then we can run also this script to see what is the standard deviation on the training data. And in this case, the values are pretty similar. It's not that bad, right? Now the next step is to calculate the root mean square error for the training and for the testing. Then we can run these lines over here. And at the end, what I'm going to do is add all the parameters that we calculated in a list, right? And that's the next thing that we are going to do. Now we can see all the values. As a summary, we can see the information that we have in this list. We have the number of nuts that we added to the model. We have the mean value for the residuals associated with the testing data when we are using the model from the training data. Also, we have the standard deviation for the residuals from the testing data, and we have the R-square for the residuals of the testing data, and we have the shrinkage, that it is the difference between the R-square from the training data and the testing data. Then we have the root mean square error from the training residuals, and also we have the root mean square error from the testing residuals. Now what we are going to do is increase the complexity of the model, and we are going to calculate again all these parameters, but with 6 nuts. Then we are going to do the same for 8 nuts, the same for 10 nuts, and go on. We are going to be calculating for different complexity of the models. We can increase the complexity of the model from 3 nuts to 150 nuts. 150 nuts because 150 is the total number of samples that we have on the training data. Then again, all the code is going to be the same, but the only thing that we are changing is the K value, okay? Here we have 12. For the next one, it is the same code, but we have 14, and we are increasing at the beginning 2 by 2, then later 5 by 5, and later 10 by 10, okay? Now I'm going to select all the sections for each nut, and I'm going to run all the code together, okay? I already selected all the code from 6 nuts to 150 nuts, and now I'm going to run all the code together. Now what I'm going to do is to take all these values for each section of the code associated with the number of nuts, and I'm going to create a data frame. It's going to be this table over here. Then I'm going to call as a table number 1, and I want a data frame with all this information. This one, for example, is for the when we have 150 nuts, and the results are this one. Then I'm going to create that new data frame, and now we can see the table. Then what we have in this table: the number of nuts, the mean value, the standard deviation, the R-square, the shrinkage, the root mean square error for the training, and the root mean square error for the testing. For 4 nuts, 6 nuts, 8 nuts, 10 nuts, 12 nuts, and go on. You can see here all the table until 150. Before I say that we have 150 samples, but we have 152 samples, okay? But until 150 is good enough. Now, before to export this table to a spreadsheet and then work with several graphs, what I'm going to do is some modifications. Here with this script, we can see the name of the rows. As you can see, we have nuts, mean, and so on. Then what I'm going to do is transpose the table, and I'm going to use this script. I'm going to add a new name for the table. In this case, it's going to be table 2. Then let's go to transpose. Now I am going to create a new one that is going to be called table, with this one as a data frame of this table over here. Then also I want to have in that table the difference between the root mean square error from the testing and also for the training. That is a new field that I'm going to add. And now I can see the new table is this table. I put it the number of nuts in this part, and I put it all the parameters as a column with the transpose option. Next thing is to export this data frame as a CVS file. Then to do that one, we are going to use this script, but we have to change the link because this link is not going to work. Then I'm going to save the name of the file as a data set, and the set that we was using in this case, it was the number 3. And I'm going to save this one over here inside this folder. Then I'm going to copy this link over here, copy, and I'm going to paste over here, from here to here, paste. And also what I need to do is to change the direction of the dash bars. Okay, this one, that's good enough. Now we can run this script to export the table. And if we go here, you are going to see that now we have a new spreadsheet with that information. Then double click to open. We are using OpenOffice, that is an open source and free software. Okay. And now we can create the graph. We have to select this column, press Shift, and also select this column. No, select this column, press Control, select this column, and then go to Insert. And we are going to insert a chart. Then what we want is a scatter plot, and we want to see, we can use this one, but maybe we want to see where the data is located, right? Then we can select this option over here. Then we can go next, and here that's okay. Next, and here we can add the title if we want to add any title, subtitle, the x-axis, that is going to be the complexity model, and also we can add here the root mean square error. Then finish, and we have already the graph created. In this case, when we are using the set number 3, the data it's not clear over here, right? Looks like it is stabilized from 100 nuts, and then it's the value is pretty constant, right, for the testing data, for the root mean square error. Here we can see that the value is decreasing because we are the model more adjusted to the data, and it makes sense, right? But for the testing data, what we want to see is a stabilized model and then goes up a little bit, right, to indicate that that is the limit. But in this case, with this seed, we cannot see that increase, right, because it's stabilized over here and gets the same values constantly, right? We didn't see any stabilization and then increase the value of the root mean square error for the testing. Then what I'm going to do in this case is change the seed and do the same process, okay? That is pretty simple, right? What we are going to do here is just create a different file, for example, for a seed number 12, and also we are going to go to the top and change the seed here for number 12, right here, and then we can run all the scripts again. I'm going to remove this one also, and this one also, and now I'm going to select all the script that I want to run, and also create the file. Then after selecting everything, now I can run. Now I get a new spreadsheet for the seed number 12, where we are using a different training data with the same original data set, right? Then I'm going to select this one, and I'm going to create the graph again. I want the scatter plot with this option. Next, I'm finished. Then in this case, as we can see over here, the minimum value is over here and then start to increase. Then I'm going to say that in this range, over here, from here to here, the value stabilized, even though 55, maybe from 60, or even we can take the 55. It's going to be around this range, right? About this range is where we have the best model. In this example, we don't have the book graph like this one, right? Let me show you. Like this one, where we can see clearly what is the evolution, right, of the model when we put the model in both data sets, right? This one is the book example, right? In this case, we don't have an example like that one, but what we can see is that the root mean square error here is decreasing, arrives this area over here where it stabilize a little bit and then start to increase a little bit, right? And that's what we want to see, right? Then in this case, I'm assuming that this interval is the best for the model. Then for the mean value, we have a good mean value for the residuals that is close to 0. The standard deviation is not that bad. The R square is really good because the model can explain around 99% of the variability of the model. The shrinkage, it's around 44%. It's not the best, but also it's not bad. And we have the stabilization of the model, right? And, you know, even this example is not the best, you know, to visualize the differences between the two data sets. We have to be ready to have an interpretation about this data. Let me close this one here. Because, you know, the first question for me is why the values stabilize over here too much and we cannot see an increase, right? Then my first point, it is, okay, is the model working well? And the answer is yes, because when I'm checking the root mean square error for the training data, what I can see is that the root mean square error is decreasing, you know? As you can see, the values are decreasing, and that's indicating that the model is changing and the model is adapting more and more to the training data over here, right? And it is indicating that the model is changing, because that we cannot see that change over here because it's pretty stable. Even more in the other case, right? In this case, it's even more stable, right? The root mean square error for the test. But as this value, the root mean square error for the testing data, it's not increasing, it's pretty stabilized, we can say, okay, maybe the model is not changing, but it's changing, right? Because you can see that one on the training data. Let me put the other graph again. Then the model is working well because it's changing. As you can see, as we increase the number of nuts, the model is changing. We can see that one on the training data, but it is not reflective at the testing data. And my thoughts here is because we don't have too many samples on the testing data to capture the small changes that has the model on the training data. As these changes are very small, as you can see, the root mean square error is changing very little, right? Then we cannot capture that change from the model on the training data on the testing data. And that's the reason because we have an stable value for the root mean square error at the testing data. But we have to interpret this information, right? And my interpretation here is that I want to stop the model where the values stabilize, okay? It's going to be over here, as I said, from maybe 55 to 70, right? 55 over here to here is where we have the best model, is where the data stabilize, and it is where we have also very low values for the root mean square error for the testing data, right? And also in this case, I'm going to apply the principle of parsimony, right? And this principle is saying the parsimony principle for a statistic model states that a simple model with fewer parameters is favored over more complex model with more parameters. And that's what we are going to apply here, right? Why we want to have a model that has a lot of parameters like this one over here if we have the same results with less parameters and less complexity? Then what we are going to take is the model that is less complex, because we have the same results, right? Even in the other one, when we are checking the other graph, here the root mean square error over here is even smaller than over here, right? But that's not the point, right? The differences are not that much. And as these differences are not that much, what we want to take is the model that provides a low root mean square error, right? But also it's not really complex. And that's the reason because we are going to take a model over here. And then we are going to use the other parameters also. We have a good mean for the residuals. We have a good standard deviation. The R square for the model is good. Okay, and when all these things are good and the value is stabilized, right, is the model that we are going to take. Also, we can support our final decision using the script related with the GAM check, right, to see if the results are good. Let me show you. For example, in this case, now we are going to work with all the data set. Okay, because now we are not working with training or testing. Now we are using all the data set. And for example, we decide the best model is the one with 60 nuts. Then after running this script, then we can check the GAM check, right? And then we are going to see that the model is good. That one is another tool that can support our final decision. Now, as we know what is the best model, the next step is to see how looks like the residuals, okay? Then in order to analyze the residuals, we are going to use the variogram. Then, as I said, we are taking all the data to extract the residuals from all the data set. I'm using this model. Then I'm going to say that I'm going to convert the X and Y coordinates to a spatial object. In this case, what I'm going to use is the backup for the data set. Remember that we created a backup, is the V2. And then we are going to provide spatial coordinates to this data set. Then we can run this one. And now we have format class spatial point data frame. Now with this script, what I'm going to do is extract the residual values from this model. And I'm going to call these residuals with this name. Then I can run this script. And with the next script, I'm going to create the variogram associated with the residuals from this model. And in this case, I'm assuming a constant value. Run. And now we can plot the variogram. And that's what we have. Then here at the x-axis, we have the distance in meters. At the y-axis, we have the semi-variance associated with the elevation of the terrain. And in this graph, what we can see is that the residuals is showing a structure. Then the residuals has spatial autocorrelation. Then we can see that the range for this spatial autocorrelation is around 50 meters. In this case, we have lags every approximately 15 meters. Now, what we are going to do is just select this area over here to be focused on the correlated area of the graph. Then I'm going to close this one, and that's the next script, right? I'm going to put the same, but now I'm going to say that I want the cutoff until 70 meters. 70 meters is over here, more or less. And I want the lags every 5 meters. Then we can run this script and plot the results. Now we can make this graph bigger and make an interpretation of the semi-variogram. As you can see now, when we are focused on the correlated area, the structure of the data, it's not that clear, right? Because, you know, looks like the semi-variogram stabilized over here, right? Then we don't have too much structure because all these values, you know, they are more or less at the same height at the variance, right? Then the structure is very poor. It's very close to the poor nugget effect, right? But still a very minimum structure in this data. Now the next step is to try to fit a model in this spatial autocorrelation associated with the residuals. Then let's go to run the next script. With this script, the software automatically decide what is the best model. Okay, we provide several models: spherical, Gaussian, etc., right, exponential. And from all these models, what is the best according to the software? Okay, then we can run this one. And as you can see, after 200 iterations, the software cannot provide a model. Okay, that is because we are very close to the poor nugget effect, and the software is saying, okay, I don't want to provide any model because for me it's not clear, right? Then what we have to do is provide approximately the values that we believe has the model, okay? And these values is the ones I provided over here. I said that approximately the seal is going to be 6, okay? Doesn't have to be exactly values. They are approximately. The model, I believe, is the spherical one. The range, I believe, is around 54 meters. And the nugget effect, I believe, is going to be 0. That's an approximation, and I provide these values to the software in order to help the software to fit a model. Then I can run this script and then see the results, and the software then provide these values associated with the model. the software is saying, okay, you have a partial seal that is 3.2. Also, you have a Nagger effect that is 0.59. Remember that the partial seal plus the Nagger effect is going to be the seal, and you have a range that is going to be 39 meters over here. And now with the next script, what we are going to do is plot the model on the data. And that is the model according to this data over here. Now, with this information, we can apply the regression Kriging, because we have the deterministic model, that is this model over here. With this model, we can predict the trend surface, and also with the residuals, we can apply ordinary Kriging to have the stochastic model. Then at the end, when we plus these two models, we are going to have the final prediction. And also one more thing. Here, as you can see, we don't have too much residuals, right? And remember that when we was talking about the assumptions of the GAM, we need to cover the assumption that it is not showing a spatial autocorrelation, right? But in this case, as you can see, the spatial autocorrelation is pretty minimal, right? And in this case, it is okay if we apply the stochastic model for these residuals. Okay, the model is not going to be that bad. We can do that one. But if you are taking, for example, a K that is lower, for example, let's go to say 50, then we are going to have more values for the residuals. We are going to have more structure, right? Because when we have here 60K, part of the structure is absorbed by the deterministic model. We can see now the example here, right? Then we can run for 50. We can run all the scripts again and see what is the final results for the... okay, because we already converted. Then we can press this one. And now we are going to plot the residuals. As you can see, now we have more structure on the residuals. Then we can be focused again on the correlated area and plot the graph. And as you can see in this graph, it is more clear, the structure, right? Before we have the values, I'm going to show you the previous graph. Not this one. This one, right? In this case, looks like we have a poor Nagger effect, right? Because most of the values are in this area. But in the new graph, we can see that in the new graph, we can see that this structure over here is more clear, right? The slope is more clear. Let me show you. In this one, you can see the slope here is more clear, and then here is stabilized. But we have more structure in these residuals, right? And when we are using GAM, we don't want to have too much structure on the residuals, because then we cannot use the model. The model is going to be invalid because there is too much spatial autocorrelation on the residuals. And that's a point that you have to consider, right? Even, for example, in this case, if you add 70K, right, then maybe you are losing all the structure on the residuals, right? We can run this example. Let's go to plot the graph. Now let's go to be focused on the correlated area. Is this one, right? Here is even less clear than we have a structure, but looks like we have something. Let's go to increase to I don't know, to 90, for example. With 90, we are going to lose everything, right? Just to have something more clear. Run this one, this one, this one, this one. And now let's go to be focused on the correlated area. Is this graph. Here we have poor Nagger effect. We don't have any structure, right? We don't have any slope of the data. It's not showing any structure. Then here we cannot apply any stochastic model because there is no spatial autocorrelation. In this case, all the residuals has been absorbed by the deterministic model. As we put here 90K, we fit the model too much on the data, right? We overfit maybe, and then we lose all the residuals. Now we don't have a structure on the residuals, and then we can apply regression Kriging because we cannot use the stochastic model, right? Then at the end, we have to look for the limit, right? We want to apply some ordinary Kriging because we want that stochastic part of the model, right? But we want also to use a good deterministic model. Then at the end, it is a balance, right? Between the deterministic model and the stochastic model. Is something that we have to be very accurate, right? With the limit between the deterministic and the stochastic. And with these tools that I show you today, you are going to have more information to have a better decision. Okay, that's the end of this video. Thank you very much for watching and see you on the next lesson.